There is this massive, almost comical paradox sitting right at the center of modern computing. On one hand, you've got an incredibly fast CPU, right? A processor that's literally capable of executing billions of operations every single second. But then, when you want to open a file, boot up a game, or load a massive database, that lightning-fast brain often has to wait for a physical metal platter to literally spin around. It's kind of crazy when you think about it. How does modern computing rely on mechanical parts without just grinding to a complete halt? Well, welcome to The Explainer. Today, we're going to unravel this engineering masterclass together.
So we know the hardware is the absolute bottleneck here, and the stakes are surprisingly high. If the operating system doesn't manage this physical traffic jam perfectly, your whole computer just freezes up. It's that simple. So today, we're going to dive into the fundamental problem of physical data retrieval, and we'll look at the brilliant, practically invisible math that software uses to bend over backwards and fix a hardware limitation.
All right, here's the game plan for our explainer today. First, we'll look inside the spinning brain of the hard drive. Second, we'll quantify that bottleneck of time. Third, we're going to solve the traffic jam. Fourth, we'll explore the famous elevator algorithm. Fifth, we'll look at how Linux practically fixes data starvation. And finally, we'll peek into the future of storage.
Okay, let's dive right in.
Part 1. Inside the spinning brain.
Before we can even begin to understand the software wizardry, we really have to map out the physical anatomy of a hard disk drive. And what's truly fascinating here is just the sheer mechanical reality of it all. Think of this internal architecture kind of like a highly advanced multi-layered record player. You've got a central spindle spinning these platters, which are basically disks coated in a magnetic material. Historically, these have ranged anywhere from tiny 0.85-inch drives all the way up to massive 14-inch platters. Hovering just nanometers, literally nanometers, above these spinning disks are the read-write heads. And they're all attached to a single arm assembly, which means when the arm moves, all the heads have to move together across the layers.
So, the crucial question is, how does the computer actually address your data in this physical space? Well, it essentially views the entire disk drive as a massive, one-dimensional array of logical blocks. And a logical block is the absolute smallest unit of data transfer. This conceptual one-dimensional line is then mapped sequentially onto the physical three-dimensional sectors of the disk. It starts at sector 0, right on the outermost track of the uppermost cylinder, and maps its way through, working inward. It's a brilliantly simple way to map a really complex 3D space.
Moving on to Section 2, the bottleneck of time.
Let's put some numbers to this and quantify exactly how much time is lost to these physical movements. This number here represents the sheer rotational speed of modern drives, 60 to 250 rotations per second. That is wildly fast for mechanical parts. In fact, it's so fast that if the read-write head accidentally makes contact with the platter at this speed, it causes what's known as a head crash, and that is physically catastrophic for the drive. But here's the kicker. Despite 250 rotations a second sounding incredibly fast, compared to your CPU, it is agonizingly slow.
So where exactly is the time going? Let's break the math down step by step. The total access latency, which is just the time it takes for your data to actually be ready, is the sum of a few different things. Step 1 is seek time. This is the time it takes to physically move that disk arm to the desired cylinder. Step 2 is rotational latency, because even when the arm gets into place, you still have to wait for the specific sector to rotate under the head. And finally, step 3 is the actual transfer time plus some controller overhead. The big takeaway here: moving that physical arm, the seek time, is the absolute biggest delay. If we want speed, we have to minimize it.
Which brings us to Section 3, solving the traffic jam.
Okay, since the hardware has a strict physical speed limit, the software has to step up to optimize the flow. There is this golden rule in systems design. Optimization algorithms only make sense when a queue exists. Think about it. If an idle disk gets exactly one request, it just does it. No math required. But in the real world, your operating system, background tasks, your web browser, they are all firing off multiple input/output requests at the exact same time. So a queue forms. And how the drive smartly sorts this queue entirely determines whether your computer runs smoothly or completely freezes up.
Let's look at the absolute simplest way to handle this queue. First come, first served, or FCFS. Check out the requested tracks at the top and watch how the disk head moves. If we just blindly serve requests in chronological order, look at what happens. The disk arm swings wildly from track 53 down to 98, way up to 183, back down to 37. It's violently thrashing across the entire platter. Sure, it's perfectly fair, but man, it is highly, highly inefficient.
So,
engineers realized they needed something better and developed the natural next step, shortest seek time first, or SSTF. And this brilliantly illustrates the difference. Just look at how tight this path is now. The algorithm simply looks at where the head is currently resting and says, okay, let's just go to the closest requested track next, completely ignoring chronological order. So from 53, it just bumps over to 65, then 67. The physical arm barely has to move, which saves massive amounts of time.
But here's where we hit a really fascinating contradiction. First come, first served is totally fair, but incredibly slow. Shortest seek time first is incredibly fast, but it has a fatal flaw: the very real risk of ignoring distant requests entirely. Imagine a scenario where requests just keep flooding in for tracks near the middle of the disk. The head will just happily stay right there, servicing the shortest distances forever. Meanwhile, a request for track 199 way out on the edge, it might get trapped at the back of the line and literally never get processed.
Section 4. The elevator algorithm.
So how in the world do we get the speed of shortest seek time without completely ignoring the edges? Well, we use the scan algorithm. I want you to picture an elevator in a busy skyscraper. An elevator doesn't just bounce randomly to whoever pressed the button first, right? And it doesn't only stay on the middle floors. It sweeps all the way up to the top, picking people up along the way, and then it sweeps all the way back down. The disk arm does the exact same thing here. It sweeps continuously from one end to the other, picking up requests along its path. It's smooth, it's fast, and it guarantees no request is left waiting forever.
Now, we can actually build an even better solution. And that brings us to C-scan on the left and C-look on the right. The C stands for circular, and here's the absolute genius of it. Instead of sweeping back and forth, C-scan sweeps in one direction and then instantly jumps all the way back to the beginning without servicing anything on the return trip. Why? Because if you just swept past track 10, any new requests there would have to wait for the entire reverse sweep to finish. By jumping back, you essentially treat the disk like a continuous circular list, which provides incredibly uniform wait times for every track. And C-look on the right? It just makes it slightly smarter by only going as far as the final request rather than needlessly hitting the absolute physical edge of the platter.
All right, Section 5. How Linux fixes starvation.
Now, theory is great, but let's anchor this in a real-world modern operating system. We need to clearly define the ultimate enemy of an OS, which is starvation. Starvation happens when a process is perpetually denied necessary resources because of scheduling priorities. Even with these clever scan algorithms, if a super heavy, localized load hits the disk, a random request can technically still starve. So the Linux operating system had to step in and create a bulletproof safety net. Enter the Linux deadline scheduler. Honestly, this is just a brilliant piece of architecture. It breaks requests into 4 total queues. First up, it gives read requests strict priority over write requests. Why? Because an application is way more likely to freeze up while waiting to read data than it is waiting to write data to memory in the background. Second, it sorts these queues using that super efficient C-scan logic we just talked about. But here's the real kicker. It also keeps a separate first-come, first-served queue strictly to check the age of a request. If any request sits waiting for more than 500 milliseconds, boom, it hits a deadline. The scheduler instantly overrides the optimization and forces that old request to be processed right then and there. It's literally the perfect marriage of maximum efficiency and guaranteed fairness.
Finally, Section 6, the future of storage. So we've spent all this time geeking out over the physical mechanics of spinning platters, but the technological landscape is actively shifting. While hard disk drives still absolutely make up the bulk of secondary storage for massive server farms and desktops, we're seeing the explosive rise of non-volatile memory, or NVM devices, like solid-state drives. And what you really should take away from this is that the intelligence is migrating. In the past, the operating system was entirely responsible for this queue management. But now, that smart scheduling is moving directly into the hardware controllers built straight into the storage devices themselves. The OS just hands over the blocks, and the drive does its own sorting.
Which leaves us with a really provocative question to ponder. As solid-state drives completely eliminate physical moving parts, meaning 0 physical seek time and 0 rotational latency, are these classic scheduling algorithms just going to become a thing of the past? Or will the fundamental math of managing queues, optimizing traffic, and preventing starvation simply evolve to manage the very next invisible bottleneck in computing? It is definitely something fascinating to think about. Thanks for joining me on this explainer, and I'll catch you on the next deep dive.